and we take a new model or project. So here we name it like dynamic model tutorial. Okay, and we select a 50 Hz grid here, and we take one generator and one grid. So here we take bus, one bus and two bus here, and we take one transformer here, we connect here, and the other side is here. And we take one grid, put the voltage source. So here the grid, we connect it here. And finally we take a synchronous machines here. So here is the synchronous machine. And now we need to declare the variables here. So first we need, for synchronous machine, we build a new project type, like say 400 MVA. And let us select it 11 kV. Okay. And then we go to load flow, for example, 200 megawatt, say 50 ampere. And let us make it a PV bus, so constant voltage, and we try to keep it 1 per unit. And next we go to our terminal, generator terminal, and we declare it as a 11 kV. Here is the then transformer, and we select new project type, to new transformer, say we keep it 500 MVA. High voltage side maybe 400 kV, low voltage side is 11 kV, and let us keep it 10%. And here, okay, and we go to and here we go to and here is log flow. So we basically declare the transformer here, and then we go to the high voltage bus, which we selected 400 kV with the transformer, and then the finally the infinite bus or the grid. So we go to line voltage 400 kV. This is connected at high voltage side, and the load flow we keep 1 per unit, 0 degree. So basically it is a slack bus, and keep it low. So it's not infinitely strong, but with some reactances here. So we go here and we have declared it. So first thing first is to just check whether our declarations working right or correctly. For that, we go to load flow and execute it. Yes, that means this steady state model is okay. Now we are into our prime concern regarding dynamic modeling. So now let us build an AVR for this generator, which will try to maintain the terminal bus voltage. And for that, uh, we need to first make a map, what we do want to do. So let's go to the mapping first. That means the big picture. So here we create a new tab here, and dynamic model, because this is our concern now, dynamic model. To create a big picture, we need to create a composite model frame where I will map my thinking or what I want to do. So it's like a almost flow chart. So let us make a composite model frame, execute, and like so we can name like a, anything. Let us write generator and AVR connecting, or generator AVR connection. So basically we actually connect AVR with the generator with a closed loop. or with a feedback system. So this is the big picture, how to connect each elements. So here, this is the composite model. Composite means there are several model. So one model is generator and one model is AVR. That's why it is called composite. We can bring other model like governor, power system stabilizer, or any other thing, any other control. If we want to bring power oscillation damper, anything. But in this example, we try to keep it very simple. So one generator and one AVR. If you know how to do this simple thing, you can build anything you want. So we keep it here. So one composite model has been created here, as you name generator and AVR connection. So to represent the generator and AVR, first we need to go here, block and signals, and we bring some slot. So basically we need two slots, one for generator and one for AVR. So we need two slots. So let us bring first one slot and other slot. There is two slot. Now let us make one slot as a generator. We need to declare another slot as a AVR. So first of all, this here. So if we select it, so these things pop up, and here we see that class name. So for representing a generator, it has a specific class name, which we need to write element synchronous machine. And how would I know what is the class name? Always go to help in the user manual. You just write class name and they will show you. For converter, class name could be like element CUNB converter. For transformer, this you need to write element TR, element transformer. So each has their corresponding class name. And what would be the class name or what it should be? It is well defined in the help function here at the top, and always prefer the user guideline. There will be everything. And this is the thing. And now what we need to do, we need to find some variables. And what to find the variables? We already discussed. You go to help functions and go to technical reference. That will show you what is the parameter name and what does it represent. For example, I'm going to show it. For example, first let us write. We want to get the terminal voltage output of the generator. So let us write UT. So UT actually means the terminal voltage. And what is the input voltage? Let us try to put some excitation as input to the generator. So BE. So BE represent the excitations and UT represents the terminal voltage. Okay. And I told that we can verify it from help function here. If we go to technical reference model, and you will see that there are some model, and if you go to synchronous machine here, if you go to synchronous machine here, if you open it, you will see that if you go down here in the manual, you will see that a lot of things written here in the input, output, state variable, and dynamic model. As we are in a dynamic model, these things, input signals, parameter is given, and what does it mean? It will be here. For example, we are using UT. UT means terminal voltage, as I discussed, and we are also using VE. So let us find VE. What does VE means? Here, if we keep looking here, VE, or you can always prefer the search function, search button. Let us write, if we don't find VE, let us write VE. So we keep searching here. Here we can find at EMT model here. If we look here, V means excitation voltage. So that's how you can find what could be the input signal and what is its function. So it's the descriptions. And be careful and be case sensitive, because you need to be case sensitive while declaring their input and output. So we are here. So actually we are taking output as a red color, which is terminal voltage, and input, which is excitation voltage. And the excitation will be given from AVR and AVR. So now one thing, if I write slot, it seems like skeptical when you work in some other cases. So let us give it some name. Generator 400 MVA. So, and we do it here. So we have declared the generator. Now the next thing is to AVR, make an AVR. So we name it like a AVR name, and the class name of it is element DSL, DIgSILENT simulation language. And we can write the name here as output and input. As this is a dynamic model, that means it user defined model. So there is no specific name, output or input, what could they represent. So feel free to write anything here. For example, I can write output signal as EFD here and input signal as, actually we are taking the input, the terminal voltage. So we can write anything here. For example, we can write UT, this is fine. But if you want, you can write B terminal. It does not matter because this is user defined function. Element, that's why it is called element dynamic simulation language. So we can name it like this, BT or EFD. So here. And now what can we do? We need to connect here, block and signals here. So this EFD is here. And this one as a feedback. So this is a control loop, closed loop transfer functions. So here is the feedback. So this is actually closed loop transfer functions. We take the feedback as a terminal voltage parameter here, and we give the input of excitation voltage to the generator. So this is a closed loop transfer functions. And now the next thing is that we know that the generator is already built in. We don't need to design generator or this thing because it is a element which is already built in the DIgSILENT PowerFactory generator. But this is user defined. We need to design our own dynamic model of AVR. Though we could select from the library, in library there are several exciter or AVR model, but in this tutorial we are going to build our own AVR. So let us now build this AVR. So from this composite model, we will go to a single model, which is of AVR. For that, we need to bring one more page here. And instead of composite model, we are interested in DSL model. So let us execute here. And let us name like AVR tutorial DSL model. Okay, we keep it like this. Okay, here. Now we need to build our AVR here, and let us try to build an AVR. I will just build the AVR with simple PID controller. So first we take input here. For that we put sum junction here, summing junction, and the left side is always input and the right side is output from the composite block. So right is output, left is input. So as we drawn like this, that the input of the AVR is VT. Now we are doing this. The input of the AVR is VT. So here from left to right. So one name appear here. So we write it VT. And it must be case sensitive. If it is a capital letter, you should write it as a capital letter. So this is BT. And we check this BT is now as input of AVR. Here we can see the VT is working as the input of AVR. So it is here. Now one more thing we need to declare here, the reference. That means what do we want, the reference. So here is for reference, we keep one signal here. Okay, so this is our reference. We have not declared it. We just name it like B reference. And later we are going to declare or uh, assign some value B reference. What do you want as a B reference? And if there is some error, that will pass through. For example, I want them to pass through a AVR. But here, if I want to take the difference, so better we assign port number one as a input function. That means the negative. And if I don't select anything at input zero, so it remains as a positive here. So this is the process to assign negation or maybe the summation. For summation, you don't need to do anything. Now let us bring a block. So if I go to library here, so there are macros. These things are called macros. And for PID controller, if we keep looking here or keep searching here, we can see here. And let us bring one PID here. So here, proportional, integral, and derivative. And there is one P to P, that means maximum and the minimum. So we bring this block here, this macros, not block, this macros. And we do like this here. Okay. Now we just connect this as input here. And this PID control output, I want it to pass through, I will give some gain. So for that, we go here and I want to select some gain here. So I go here and here's the multiply gain. So I will multiply this with some gain. So here I keep it and I connect this with connecting arrows. So here, from here to here, and this. And then I will pass it through a integrator. I want to pass. You can do anything. You can. It depends how you want to design. I'm showing one of the examples, or then I want to pass it through mm, a leg function, first order leg function. So here I go. This integrator. We need no filter. Yes. So in the filter we can not high pass, low pass filter. First order leg low pass filter. So I take one low pass filter here. So I take one low pass filter with a limit and I connect it. And then I go further here. And then I want this processing to stop here. So I take this here and I want to pass it through one integrator. And for that, we go here. So we keep looking, we keep searching here for an integrator, limiters, integrator here. If we go there, we will find 1/st here. So we take with the wind-up limit, that means it will have a wind-up limit, that means upper limit and lower limit. So for that PP, 1/st PP we need, yes, here we can see 1/st PP. So it has upper limit and lower limit. So we connect this here and the output will be as exciter here. Now here I need one more thing. So it should be, the output should be B. For example, the output is EFD, sorry. The output signal is EFD. So we keep it as EFD. So we keep as EFD and it should be case sensitive. And one feedback, we need to put one feedback here through a gain. So better we first find a gain here. So we are looking for a gain here, and multiply again. Okay. So we bring again here and connect it, the feedback gain. It's not unity. I am putting some gain here. Sorry. Because this is the input side. So that's why it was not connecting with it. So we connect here. So input, we provide the input at the input terminal and the output from this here, here, and here. Okay. So the structure has been built here, and so this is the AVR structure. Now, one thing we should do here, we need to initialize these things. We need to put what should be the starting point. That means the stability point. For that, what we do, we put dx by dt. That means any kind of derivatives or change equal to 0, which is in frequency domain or Laplace transformation represented by S parameter. So if we put S equal to 0, we can actually find the initial condition of these things. Okay, before we go there, we can do one more thing. Actually, we are measuring the terminal voltage and providing it here. But we know that the measurement is done by some transducer or sensor, and they have their own processing time. So let us put some first order lag functions. That means some measurement delay here, because it will be then more realistic. So for that, we provide one filter here. If I keep looking here, filter, limiters, you can always minimize these things so that it will help you to, here is the filter. So low pass filter, which means actually a lag function. So 1 by ST. So we put it here and let us disconnect this one. So here it is, and we connect it again. And here this one. For better appearance, I bring it here and shrinking it a bit. So this is actually a first order lag function. Okay, this is a first order lag function. We can actually zoom in. Yes. So from here, the output is here. We can shift this to have a better view. Now, and bring it here. This thing is open, so we need to draw it again. Connection. So 1 by ST, and we take it here. In one of our lectures, these things happened, and we could not run the model that time. Okay, so it should be declared as B terminal, because we know that the input of the AVR is B terminal. So we are case sensitive here, and we declare it. And this is these things. Now we can actually, because there are some names. For example, we are using this first order like here, and we use it one integrator here, one PID controller here. So they have their respective times This first order has their time, this PID has its time, this integrator has its time. So let us better give them some name so that it is easy to pick them up. Let us start this with R, TR, and we keep it XR. Okay. And then we don't do anything here. Better we write the state variable as integral and here derivative. And we know that what are the state variables? State variable means the output, xi, xd. That means state variable means the output here, xi and xd, because this is a PID controller, so the output is with some integral and derivative actions here. Because it is connected to S. If I put S, that means there is some dynamics S. Proportional does not have that. This is a proportional. So this is like a gain. But here for integral and derivative, there are S functions. That means they are dynamics in nature. So they have the output. So we name it like xi to represent the integrator and xd to represent the derivative. And this is one gain. We better name it A. And this is one first order leg. We name it like B regulator. We omit it and B regulator because this is the regulator and it will further give the signal to the exciter. This is, we are now processing the regulator, and the regulator will give the signal to the exciter so that it increases the excitations, field current. So this is TR, we name it like XR. TA, we name it like X, we better name it A. So these things are here. Now we go here. We name it like BE because this is the or EFD, field excitation maximum, or EFD minimum here. And one thing is very important here. What does this parameter means? Parameter means you can take the input as a runtime. We will see that. We will see this. So here we write, we name it like E, TE, and KE. There is XE as exciter, so we E. And there is, we name it like E because this is a feedback of exciter, so KE feedback or whatever you can name it like EP. It depends on you, random name, but you should be strict. If you put this name, you need to follow all through. Whatever name you can put, but you need to follow all through because these are case sensitive and you need to also maintain these letters or what. Okay. And here uh, here the input is 1, we can really subtract the feedback, or depends on your design if you want to give negative feedback or positive feedback. Now the next very important thing, initialization. We have actually constructed our AVR, but now we need to initialize at time equal to 0. How should it behave? And for that we put s equal to 0. For example, if we put s equal to 0, 1 by st. So what actually happened? If we, for example, here 1 by st, 1 by 1 plus st, and this is not actually tr because we have named it the t as tr. So if we put s equal to 0, what happens? 1 divided by 1, that means 1. So it becomes 1. So what is input? Equal to output. That means at initial conditions, this is equal to bt. So this output, that means it has a state variable which is xr because we name it xr. We can check here. See, the state variable is xr. So xr, that means the output equal to bt. For that, So we have found the initial condition for this block. So we can click in any empty spaces here. If we double click here, anywhere, but in the empty space, we double click the left mouse button, their equations, and we need to initial condition, because at t equals 0 it represent initial condition, and after t greater than 0 it becomes increment. This inc means include initial condition when t equal to 0, and this inc also means increment when t is greater than 0. Now we have found xr, because xr equal to bt. That's what we have found just now. xr equal to bt, because it becomes 1. Now here, when I put s equal to 0, then we can find several things here. What are the state variables here? xi and xd. Okay. So actually PID, that means there are three parallel things, P, I, and D. And we know that with integrator, S is 1 by S. So it becomes infinity. And derivative S always comes as a multiplications. In example, if I go here, integrator comes as 1 by S. So if I put S equal to 0, it becomes infinity. Infinity at initial condition. And derivative comes like this, okay, so with some gain. If I put s equal to 0, it becomes 0. So that's how we can find the initial condition here. So if we put s equal to 0, it will be connected all the way here. So let us come from right hand side. So from right hand side, we can see that if we put, to come here, we need to first go to right, and from right to left, we can easily find out this. So better, before determining PID controller, we find this one, so that we know what is actually progressing or have been taking a regression here from finish to start way. We better say regression. And so this will be the preference way with the regressions, so that we can find what are there. And we also need to declare this. We need to know about this parameter as well. So if we double click here, the state variable is xc, and this comes as an integrator function. So if I put s equal to 0, it becomes open circuit, because infinity. That means this output equal to EFD. That means x equal to EFD. So we have found this condition. So we write here. Whenever we find the conditions, we write here. So this is xc equal to EFD. Okay. And then we check the second last, this one. It does not have any s function, so we don't need to declare this one. And we have this one, 1 by st. So if we put s equal to 0, it becomes this. So 1. So it becomes 1. So what is the output here? Actually, the output is from here, KEEFD, because the EFD is multiplied with this feedback KEEFD. This is the state variable of this TF function. So this becomes KEEFD. So we can write here. What is the state variable? X. So we have found the condition of X as well. So we go here, increment or initial condition X E. Sorry, what is the name? We need to go here, X. So here again, so X equal to KE. We need to be case sensitive, big capital letter K, KEEFD. Okay. And we don't need to do anything for this, because this is already there is no S. And now we go where we need to declare xi and xd, as we discussed. So xi equal to, actually, if I go here, we can see there are two stable xi and xd. Here, if we see here, actually, what was this xa? If I actually relate it from here, we see that xa into Ka equal to the output of this. So we can write like this. If we go here, if we look here, we see that the output of this function is Xa. So Xa into Ka. That means what is the output from here equal to the input. What is the output here? We can find it from here. Xa into Ka. So the output here is actually the output here is Xi, because only the integral will be active and the derivative is zero. We discuss about the derivative is zero, so we cannot expect the derivative to have an output in initial condition. Only the integral is active. So the Xi output equal to Xa into input. So we can see like Xa equal to Xi into K. That means if there is X output, Xi equal to there is Ka into Xi, because this is the output here. So Xi into Ka will make the output of this Xa. You can relate it from here. See, this is the output Xa and X equal to the output of here Xi. It passes through this gain. So the output is Xi Ka. So this Xi Ka will go through this because s equal to 0. So what is here? It will simply passes through this, because in initial condition, the multiplying factor here is only 1. Because if we put s equal to 0, it becomes 1. And from here, we expect that Xi as output, because only the integral remains active here. So Xi into Ka equal to Xa here. So from here, we can see that Xi equal to Xa divided by Ka, and it should be essentially Ka. So bigger letter Ka. So that's how we find the condition of Xi. Xi equal to Xi divided by Ka. Let us write this. So equations here, in initial condition Xi Xa divided by Ka. So we have declared this. And what about the xd? We have said that xd equal to 0, because in initial condition for the derivative, if we put s equal to 0, the total term is 0. So at initial condition, we don't have any output from the differentiator. So we expect that in initial condition, xd equal to 0. So these things are declared. Okay. Now one more final thing, B reference. What do we want? What is our expectations from the controller? So we declare it B reference. So equations here, increment B reference. Sorry, it should be breakage. B reference. We want it to be, for example, we want to keep it BT. That means what we initial condition, we want to keep it like BT. What is the terminal voltage? We want to maintain it. Later, we will verify our AVR with putting some disturbances, creating some events. It will come. So we have done these things. Now the next things is to declare these things. What we have built now, we need to declare these things. And remember, all the things are in parameters, so they will appear as a runtime input. Now we need to go here, because we have done this. We have created the big picture here, the composite model, and we have built the individual model here. Now what we need to do, we need to interface this with our model, this model. Here, this model. We need to interface this with the here, generator and this model. For that, we need to go into our data manager, because we need to create some data to declare these things here. And if we go here, this is our active project here. So we go here on the left, we create one new object here, and we go to a composite model. So here, if you write, one composite model will appear. Okay. And from here, we go to frame, select type, composite model frame. Okay, here. If you go here, we see there are four options: OK, cancel, DIgSILENT library, or project library. We will prefer this project library, or it is already here. Project library, it's already selected because we have built the project of our own. Otherwise, if we don't want to build our own project, we could select it from DIgSILENT library. But the problem is that you cannot do many things there because this is already built in. But if you want to build your own, it is here under the project library, because what we have done those things just a few minutes ago, it is already here in the project library. So here we select the composite model we built. So we go here and okay. Sorry, AVR has been selected. We go again here, select composite model, this one. We need to select this one, generator and AVR cursor, because that composite model we built. Okay. So here is the frame. So you get the frame in your model, dynamic model tutorial. So let us first declare the generator 400 MPa. For that, we put our cursor and double click. So the synchronous machines appear here. Okay. And for AVR, if we go here, we see that the AVR is not here. So for that, okay, we keep it here. Okay. Then we go to our things here, and then we go to here in the network model manager, go to create. Uh, Better we go to this data manager here. And if we look under the project here, dynamic model tutorial, the network model, and we go to network data here, the grid. Here we need to bring, because in the network data in the grid, we have these things, but we need to bring the composite model here. So here we go, composite model, okay. And here we need to select type, composite model type, and here is our selections here, this one. So you go here, okay, and the generator we need to select this one, and here in the AVR we need to select here from again this one, the plus and new object here, and DSL model, because we did not do anything with the model command. So if you go to DSL model here, and we need to select the type, select type because it is already built in. We need to go to project library here, and because we did build of our own, so it should be from the project library, not the DIgSILENT library. DIgSILENT has a lot of etc, but we don't are interested here, at least for now. We are here in project library. We go to AVR tutorial because that was built by us. So here, okay, and these things appear here. Now, as we discussed that all the input will come as a runtime input. So these are the input. You can put the input here or after declaration, no problem. Uh, so let us put the input here. Let us put some input. Uh, and now we put KP equal to 50 here and Ki equal to 5 here, Kit equal to 20 and TD equal to 0.1. Actually, how I am putting this value, it depends on the design. So you need to first tune these things, and this is not the scope of this tutorial. And KA here. So For example, K1 TA equal to 0.01, T equal to 1.2, K equal to 1, TR is equal to 0.02. We have not changed one name, Y minimum and Y maximum. Look at this. We put these things BR minimum 0, BR maximum maybe 5 per unit. That means our BR minimum by -5. EFD minimum is 0 or EFD maximum is like 5. We can actually give good margin to the regulator. Understand. And what are Y min and Y max? We can see it from here. And as we declare this, we are sure that these things are declared. That's why there is a tick sign. Otherwise, it will be as a negative sign. Now it is a tick sign. So that means they are declared. Okay. So here and if we go here in the synchronous machine, this is actually here. So there's the DSL model, and these things we had to declare. Okay. Now, one thing we saw that what were the Y minimum and maximum here. So here we better write it like PID maximum, B, PID maximum, so that we know what does it mean if they have their own name. You can name anything, but as we do like this, we know that what is their name. So if I go here again, so DSL, and we can keep then B PID means like -100 and PID max maybe 100. So whatever the output from the PID -100. Okay, so these things are declared now. Okay, okay. So we have done these things, and to observe the runtime output, we go here, diagram. So this is the dynamic output. Now let us check what happened, whether everything is right or not. So initially it takes time because 0% here. Yes. So if not no error signal appears, that means everything was right, and we can check the output from here, and we can check it here, generator and these things. So we run it here again, this one. Okay. So the dynamic model has been completed, and here we can see the runtime input. So the terminal voltage is 1 per unit, and the EFD here is 1.43. That means we are actually providing some excitation voltage here in the generator from AVR. And what is the AVR? This is the AVR. And we can also observe the AVR from runtime. For that, we go here in the AVR, we go diagram, we go to diagram. So you can see the runtime input of this AVR. So we are actually receiving the terminal voltage as 1, and our reference is also 1 as we declared. We will see how to change this reference and check that it is also working. The AVR is also working to achieve the set point. But as both are 1, so you get difference is 0. And to maintain the 1, there is EFD 1.43 is needed. So that's how we can see that yes, our own AVR is working here. So now let us finalize it. We bringing some parameter event here. Okay, we stop here. Now let us make one parameter event. So here we go, and we here parameter event. Okay, here and element here select. So from AVR we want to select B reference, name of the variable B reference. New value, say for example 1.03. We initially put it 1. Now we are creating some disturbance to check whether our AVR is working or not. So we put 1.03 at, for example, 60 seconds. So this is my event. And if my AVR is working or try to take some initiative, we can observe this. And to check the voltage, we take one output from here, result variable here, simulation or here. So from here, we try to observe the positive sequence voltage, positive sequence voltage. It is already here or not? We select positive sequence voltage here, U1, U1 in per unit. So we better find it in power here, positive sequence voltage. So we select this positive sequence voltage, close. We go into the plot here, and we want to plot page execute. So here, if we go here, insert plot, there is a card plot, okay. And here element synchronous machine and variable is pass voltage, okay. And now we insert rows. Uh, we see that here we see that the AVR parameter is not declared. So we go here in the grid here, and here if we go here, result variables, simulation, and if I go here, and I don't know where to find the object or these things. Uh, for that, the easy way to go to object always, and here you can find select. From there, you can select whatever in your grid. So you can find it here. And for example, if I go to AVR here, and you can see all the design, all the parameters or parameters are here. So you can select anything here. So like we are interested in field voltage to see the field voltage, how they are working. So we can see BFD or EFD. We can see the output EFD here. So here we can find EFD. So okay, here. So these things also selected result variables. And okay. So this result variable is also selected. So if we go here, insert plot, okay. And from here, we can see this DSL model is already included. Okay. And we can see we need to select one more variable, result variables. This is generator terminal voltage. So synchronous machine, positive sequence voltage. So U1 positive sequence voltage here, U1 positive sequence voltage. Okay. So these two things are in result options. So we'll find that. Okay, here. So if we go to plot page, if we go here, now DSL model variable is EFD here. And we need one more row to select, to observe the synchronous machine's terminal voltage U1. And we go here. Now, before executing, we go how long time we want to run it. 200 seconds, execute. And if we refresh this one, we can see uh, that magnitude synchronous machine voltage magnitude is in per unit, it's decreasing, and this is decreasing these things. So so that we are found that, or we have been confirmed that the model is actually working. That's why if the disturbance takes place, this is reducing. Now we want to